Okay, so we're getting into techniques for integration. Last video we saw using U substitution. This time we're going to talk about integration by parts. So this is integration by parts. Now, what we're really doing here, it looks like pants, that's an R, parts. What we're really doing here is we're undoing the product rule. So recall, if I take the derivative of f of x times g of x, that is first times the derivative of the second plus the second times the derivative of the first. All right, so what we're going to do is we're going to take the antiderivative of both sides here. Okay, so if I take the antiderivative of the right-hand side, I'm going to get the antiderivative of f of x times g prime of x plus g of x times f prime of x dx. And if I take the antiderivative of the derivative, I just get back the product. Okay, so this can be broken up. This is the antiderivative of f of x g prime of x dx plus the antiderivative of g of x f prime of x dx is equal to the product of f and g. Okay, so not so bad. I'm going to move something over here. I'm going to take this piece here and I'm going to just move it to the other side. So f of x times g prime of x dx is equal to f of x times g of x minus the antiderivative of f of x times g prime of x dx. So we're going to do a let here. We're going to let u be f of x, and we're going to let v be g of x, right? So if I kind of think this through, I'm going to get that du dx is f of x. So this implies that du is f of x dx. And likewise, I can say that dv is g of x dx. You can follow the same logic there. So let's do some simplifying here, right? Sorry, this should be f prime g prime. There we go. So this means that this integral is going to change to u times dv, because dv is g prime of x dx, should be u times v minus the antiderivative of, well, let's see. Oops, there's an error here. I moved this over, right? So this should be, let's get rid of that. Excise that, delete it. What should that say? All right, so that should say, what did we move over? We moved over the antiderivative of g of x times f prime of x dx. There we go. So g of x is v, f prime of x dx is du. All right, so this is my critical formula. The integral of u dv is equal to u times v minus the integral of v du. You need to know this. Like, write it on your forehead backwards so you can see it in the mirror in the morning, something like that. But you need to know this thing, because this is like a really key formula. Like, if you look at it in your notes, I even found a way to make it look like orange. Okay, because it's so important. All right, so let's see an example of how this works. All right, so let's say I want the antiderivative of x sine of x dx. Now this seems like something that's innocuous and should be really simple, and it's not. Okay, so you can try to throw everything you got at this, and you're going to run into some problems. So what we're going to do here is we're going to let u be x, and we're going to let dv be sine of x dx. Okay, so this is now the integral of u times dv, which is the left-hand side of my all-important formula. All right, so on this part, we're going to take the derivative. We're going to go du dx is equal to 1, which means that du is equal to dx. On this side, we're going to take an antiderivative. You're going to get the antiderivative of dv is the antiderivative of the sine of x dx, which means that v is the negative cosine of x. Okay, so I use my formula. My formula says the integral of u dv is equal to uv minus the integral of v du. So this means that the integral of x sine x dx is u, which is x times v, which would be the negative cosine of x, minus the integral of v, negative cosine of x, times du, which is dx. So this is going to simplify to negative x cosine x plus the integral of the cosine x dx, which is negative x cosine x plus the sine of x plus c. And there you go. We have taken the antiderivative by using the by parts formula. Big fun. All right, so let's look at a second example, something that's seemingly innocuous but a little more tricky. Okay, so you have that like the integral of 1 over x is the natural log of the absolute value of x. But here I'm going to say, what is the integral of the natural log of x dx? What's the antiderivative of the natural log? This seems simple, and yet it is not. So we're going to use our idea of by parts. So let u equal the natural log of x. And we're going to let dv equal dx. All right, so in this one, we're going to take the derivative, du dx is equal to 1 over x. So du is equal to dx over x. That's pretty straightforward, right? And then here we're going to take an antiderivative. So the antiderivative of dv is equal to the antiderivative of dx, which means v is x. Okay, so that's not so bad. So I use my formula. The integral of u dv is equal to uv minus the integral of v du. Well, u is the, let's see, so this is the integral of the natural log of x dx is equal to the natural log of x times v, which is x, minus the antiderivative of v, which is x, times du, which is dx over x. Now, lucky for me, these x's cancel. So I get x times the natural log of x minus the derivative of 1 dx is just x plus c. All right, so the antiderivative of the natural log of x is x times the natural log of x minus x plus c. And we got that by using the by parts formula. Now, when you're doing this with a definite integral, it gets slightly more complicated. All right, so let's say I have the integral from 0 to 1 of the inverse tangent of x dx. All right, I don't know the antiderivative of the inverse tangent. I know that like the antiderivative of 1 over 1 plus x squared is the inverse tangent. This is the other way around. So I'm going to let u be the inverse tangent of x. And I'm going to let dv equal dx. All right, so du dx is 1 over 1 plus x squared, which means that du is equal to dx over 1 plus x squared. The antiderivative of dv is the antiderivative of dx, which means v is equal to x. All right, so I have the integral from 0 to 1 of the inverse tangent of x dx should be the inverse tangent of x. So u times v, and this is from 0 to 1 minus the integral from 0 to 1 of v du is dx over 1 plus x squared. All right, so let's deal with this piece first, right? This is going to be the inverse tangent of 1 times 1 minus 0 times 0 minus the integral from 0 to 1 of x over 1 plus x squared dx. Okay, so the inverse tangent of 1 is pretty straightforward. Let's see if I think about this. Where does the tangent equal 1? Well, that's at pi over 4. Right? So this is pi over 4 minus the integral from 0 to 1 x over 1 plus x squared dx. All right, so let's get some more space here because we got a little ways to go yet. Actually, let's not do that. Let's take from here down, right? That way we could see what the original problem was at the end. All right, so right now we're sitting on what? We're sitting on, so far we have this as pi over 4 minus the integral from 0 to 1 x over 1 plus x squared dx. Let's clear this all out now. Okay, so we're in better shape. All right, so the pi over 4 is just going along for the ride. We have a minus. Oh, wait, let's see what we got to do here, because this is now a u substitution situation. Since we already have a u in play, we'll call this u2. We'll let u2 equal 1 plus x squared. du2 dx is going to be 2x, which means that dx is equal to du2 over 2x. All right, so playing the u substitution game here. Well, let's see. If we put 0 in this, we get 1. If we put 1 in this, we get 2. We have x over u times d, that's u2, over du2 times 2x. The x's cancel. Gives me pi over 4 minus 1/2. The integral from 1 to 2 of du2 over u2, which is pi over 4 minus 1/2. And this is going to go to the natural log of u2 from 1 to 2, right? So this is pi over 4 minus 1/2 times the natural log of 2 minus the natural log of 1, which is just 0. So this is pi over 4 minus 1/2 times the natural log of 2. And at that point, as ugly as that is a constant, and that is the value of this definite integral. So if I'm thinking about what this is actually saying, if I graph the inverse tangent, right, and I take the curve from 0 to 1, that space, this is the value of the area under that curve. That's pretty cool. All right, so there you go. There's something to chew on for integration by parts. We'll do some work on this in class.